This meeting is being recorded.
Okay. Yeah, so welcome back from fall break. Sorry that your greeting was a quiz back from fall break. But I know a handful of people mentioned that there was confusion about whether there was going to be a quiz or not today because of the strikeouts here in the last week. So I will think of something that we'll maybe be able to make that up to people who were surprised about the fact that we had a quiz today. But I don't have anything right now. I've got a handful of administrative things that we will go over. Basically, we'll go over everything until the next midterm here. And then we're going to be going over this Chapter 3 linear models sheet. I passed that out before break for those of you who wanted physical copies. If you're looking for the electronic spot, it's this notes-linear.pdf that we'll be going over. But administrative things. So first here, quiz next Wednesday. This will be on the Chapter 2 stuff that is not just definitions, but actual problems and reasoning. The practice file looks like this. There's a printed copy up here for those of you who want the printed copy. Link to the practice file right here. And also there's a answer key, like usual, to this practice quiz. The main thing that'll be different about next week's quiz will be that it will be worth double points. Motivation for that is because the material here is getting very important and also very difficult, and want to reward you all for putting in the time to study the difficult material. And so it'll still be 4 problems, same size of the quiz, just the values of everything will be doubled. So 2 points for the correct answer, -1 for the incorrect answer, and then 0 for the blank answer. We are currently starting Chapter 3 in the textbook. This will be the last chapter in the textbook that we do before your next midterm. So we will do this for this week and the next 2 weeks. And the midterm will be the first week of November. It'll be a similar sort of format of sign up for time slots that work for you. So that's your, I guess, time frame of when to expect that. 3 more notes packets, including the one that we'll be going over today. So just to have an idea of how much more stuff. And then last administrative stuff down here. So again, the next week's quiz next Wednesday is Chapter 2 quiz. Chapter 2 quiz next Wednesday. We'll have a Chapter 3 quiz the Wednesday after that. That'll also be a dedicated midterm review day, and you'll have a programming homework for Chapter 3 that will be due on November 3rd. So it's just heads up about all the upcoming due dates for things. Any questions about anything administrative? Upcoming things going on? Okay. Everybody just wants to, it's been too long away from math over fall break. You guys just want to dive right in. I like it. Good job. So we're going over here on the Chapter 3 linear models notes. And again, where this is electronically is this notes-linear.pdf. And there's, well, first I'll talk a bit about a high level of where we're going. The Chapter 1 introduced all this definitions about things. We didn't talk too much about the theorems or things yet in Chapter 1. And then Chapter 2 talked about the statistical properties of machine learning, and in particular, this VC dimension and the VC dimension bound, the 2 most important things from Chapter 2. But we didn't talk at all in Chapter 2 about how do you actually do the learning process. In Chapter 1, we saw the PLA, the perceptron learning algorithm, and then there was this T algorithm, the try everything algorithm. But the PLA is specific only for one particular hypothesis class, and it's also specific for the linearly separable case. The T algorithm is only for finite hypothesis classes. And so now in chapter 3 here, we're going to be talking about the computational aspects of machine learning, the algorithms for selecting a good hypothesis in the hypothesis class. And that's what this motivation section up here is saying. There is, I apologize for this a little bit. There's a lot of text right here in this this first page of this notes packet. Actually, this whole notes packet has a relatively high amount of text in it. The motivation for that, the reason for that is because there is some sloppy notation, in my opinion, sloppy notation in the textbook. And so in the textbook here in chapter 3, if we come here to definition 1 right here, they redefine our E sub n to be this new equation like this with an L inside of it. When they redefine our in-sample error like this, they're not defining it. They don't put this superscript L up here. They just say E sub n is now equal to this new thing over here. And I think it makes it a little bit confusing to talk both about the old versions and the new versions at the same time. And so I wanted to have for you all just a reference here that's printed out that you know there's no mistakes in it about what the notation is that I'll be using. So I'll be using this new notation up here instead of the book's notation, again, because I think it's a little bit more explicit, a little bit more clear. But you are free to go back and forth between whichever notations you like, whichever one is more clear to you. In order to explain this notation here, I'm going to use this blank space down here to actually walk through what the notation is doing. And I'm not going to directly talk about this stuff up here. I'll just leave that as like a clean reference for you so that you know like there's no typos in this part up here. But so recall that our in-sample error, E sub n, was originally defined to be something like 1 divided by n, sum I equals 1 to n of this square brackety thing, the indicator function of h of x sub I not being equal to y sub I. And it turns out that in this section and vast majority of machine learning stuff, it is inconvenient to have to always be comparing our, so this right here, this h of x sub I, this is our predicted value. The h right here is our hypothesis. This is the y value, what we are predicting our hypothesis is going to be on the x sub I input value. And it's inconvenient to always be comparing this with like an exactly equal to or not equal to. That in other situations, there are more convenient things to do. And so this, the first thing that this section of the book does is it introduces this idea of a loss function. This sort of scripty cursive L will always be used as a loss function, not just in this textbook, but this is a very standard thing in machine learning. This is one of the few things that is standard in machine learning, is that the scripty L is always a loss function. Loss function. And the loss function that's being used up here is the 0, 1 loss function. So I'll write it in blue like this so that, oh, we'll do a different color. We'll do red. We'll do L 0-1, or I'll make that a subscript instead of a superscript, 0-1 of y hat comma y is equal to this square brackety thing. H of xi not equal to y sub I, like this. Well, sorry, let me undo this. This h of x sub I too is often referred to as y hat sub I. So the notation used in the textbook is at this point is y hat not equal to y. In general, anytime you see a variable that's wearing a hat, that means that that variable has somehow been estimated from the data. A variable that is not wearing a hat is generally somehow not related to the data, but a variable wearing the hat estimated from the data. And so these loss functions are always going to take two things as input. our y value that we estimated from the data, the y hat, and the true y value, and it's going to give us some sort of numerical score about them. Based on this loss function right here, this 0, 1 loss function, we can rewrite E sub n. So I'll do a superscript up here, superscript L, as that is equal to 1 over n sum I equals 1 to n. Now in here, it's going to be our generic loss function, whatever it is that's comparing our y hat sub I to our y sub I value. And again, the y hat sub I is equal to h of x sub I. Those two things will be used interchangeably in the textbook at this point. Substituting this L01 into this equation down here recovers our original in-sample error, but now we have this additional flexibility that we'll be able to use different loss functions in order to measure our in-sample error in different ways. And we will see that we will need to do that in order to be able to actually create algorithms that can minimize the in-sample error. So everything that I just said down here is, again, just sort of a restatement of this stuff up here. But if, again, you missed anything down here or want to read a text version of that, that's what you have a reference up here to look at. Any questions so far? Is this, I don't know, waking up your mind, getting you back into data mining mode a little bit, hopefully? Question? Yeah.
You said that the new bottom equation in Start provides additional flexibility. Is that additional?
Yeah, so this red equation right here, well, yeah, start right here. So this thing is like a generalized version of this up here. This in-sample error is just a generalization of this in-sample error up here, where we can provide whatever loss we want. Exactly. There's a handful of things that get redefined in a similar way like this throughout the chapter 3. But chapter 3, there's not going to be any sort of quiz on definitions because these definitions are basically the same as the chapter 1 definitions. And I don't think it's too much work to just, or you'll sort of naturally memorize them just by reading the things. You don't have to sit down and necessarily memorize these. A good question. Okay. So why do we do this? In chapter 3, the first 3 sections, 3.1, 3.2, and 3.3, they explore 3 different loss functions right here and the learning algorithms that correspond to those loss functions. The notes right here starts with section 3.2 instead of 3.1 because I think this is the simplest section and it's the easiest section. Here, this is using the squared loss, section 3.2. And this is also related to everything that we've seen so far has been binary classification. So everything so far has been binary classification. And so in particular, the output set y, they use the script y here, has always been equal to -1, 1. But now we're going to be using y is equal to the real numbers instead of now y equals the real numbers instead of the binary classification. So that's what makes this a regression problem. And a very popular model for regression, the standard one is called ordinary least squares, or OLS for short. And this is the hypothesis class that's associated with ordinary least squares. This should look like a very familiar hypothesis class, that all the important parts are really the same here, that we have The size of this hypothesis class is infinite. I know that because in here, when I look at this colon, looking to the right-hand side tells me how many things are going to be inside of it. And this W here is contained in R to the D. Our weight vector here is contained in R to the D. And so there's an infinite number of hypotheses over here. Each one of these hypotheses, or each one of these functions, is determined by a linear function here, W transpose times X. And this is the exact same thing that we had in the perceptron, except there's no sign function. Only difference between this and the perceptron is there's no sign. Otherwise, same as the perceptron. A lot of the theory between the, well, let's see, let me back up. The reason why we're talking about the squared loss now is because it's somehow the simplest possible way of doing regression. These linear functions are like the simplest things you can possibly do. And the reason why we started with the perceptron is because it's like the simplest possible thing that you can do for classification. These linear functions here, dot product, W transpose X, like the simplest possible thing. So there's a lot of the intuitions that carry over, or that you may have developed about the perceptron, they will carry over to the squared loss here and ordinary least squares. Or if you've taken a stats course before, seen ordinary least squares, a lot of those intuitions carry over to the perceptron. The so new thing down here is this squared loss, this L function of y hat comma y equals y hat minus y squared. This is the key thing that's going to be new here. The key new thing. And so I'm not going to write out, I guess down here I did write out our new definition of the in-sample error with this squared loss. Looks like this. We still have the 1 over n, the summation from I equals 1 to n right here. And then this thing right here is just our L value right here, our squared loss. And again, in particular, this xi transpose w, that is, we have several notations for this now. That is equal to the h of x sub I and also equal to the y hat sub I. All those notations used interchangeably. Why is this equal to h? In this case, again, our hypothesis comes from this hypothesis class up here, where all the functions have the form w transpose x. So it's just that w times the xi transpose. In this case, they're written in reverse order, but the dot product's commutative, so that's equal x transpose w equal to w transpose x. One of the things that is common to do in least square stuff, especially in like the statistics community, is to take this equation on the left-hand side and rewrite it as this thing over here in matrix notation. So this is just matrix notation of En. And very common to see the in-sample error written in either form for ordinary least squares. The reason why the textbook is talking about ordinary least squares at this point, though, is related to problem 1 right here, the first thing that we're going to really have to do in class here. And that's that, how do we find the minimizer of the in-sample error for ordinary least squares? It says the OLS model is convenient because the hypothesis G, which minimizes En, can be computed in closed form. So show this computation. So first of all, it says, so G, which minimizes E sub n, so we want G equals the argmin over H in our hypothesis class of E in of H. Here, I'm eliding the dependence on the squared loss right here, not writing it out. But because it's understood that we're using the squared loss right here because we're talking about least squares regression. But you could, if you wanted to be more clear, saying L of the squares right here, least squares, the squared error. But I'm not going to be able to fit that, so I won't even write it out at all. Substituting this in, that's equivalent to the arg min over w of this equation right here, the x w minus y squared. I've done two things when I did this substitution. The first thing is, notice my arg min down here is now over w instead of h. Very common when you're minimizing. So minimizing w is equivalent to h, equivalent to minimizing h, because in our, I'm going to scroll up just for a second here, in my hypothesis class definition right here, every w defines a unique h, and every h is defined by a unique w. So it's very common to just go back and forth between the h's and the w vector. And the textbook does that without even explaining that they're doing that. The formal thing to say is that there's a bijection between the h's and the w's, and so you can treat them interchangeably. But if you haven't heard that word before, that's fine. It's just every h has a w and every w has a corresponding h, and so minimizing the w is a fine thing to do. On the left-hand side over here too, I'll say that this is w hat. Again, the hat on top of the w indicating that it's estimated from the data is equal to this whole thing over here. The other thing that I've done for like notational convenience is put a single vertical bar right here instead of the double vertical bars with the L2 notation. And this is anytime I'm writing out matrix formulas by hand, I will use single vertical bars to save myself a lot of writing and to make my notes easier. But this is still the same, L2 norm, and just changing how I'm writing it to be a little bit more convenient to write it out by hand. From calculus, we know that the way that you solve one of these minimization problems is you set the derivative to the inside over here equal to 0. So we say 0 equals, take the derivative with the thing that I'm minimizing with respect to. So I'm minimizing with respect to w right here. So dw of the thing inside, x w minus y squared. And then at this point, it's a calc problem of computing this derivative. A lot of people maybe haven't seen derivatives of these like fancy matrix vector norms before. If you're in that case, there is this website, matrixcalculus.org, which computes all of these derivatives for you. You're welcome to use it on any of these problems. I don't have it open already. Matrixcalculus.org. Wolfram Alpha will not work on these sort of problems because Wolfram Alpha does not support matrices or vectors, anything multidimensional. But this website right here will. If you are using it, you just have to be careful that the matrix here, it's defaulting to being a symmetric matrix. We just want a generic matrix. And if we change this x to a w, then and taking with respect to w, this is our derivative right here. Actually working through this, the way the derivative turns out to be is it's mostly what you would expect. The 2 is going to come down, the 2 comes down, then you take the derivative of everything inside here. We're taking the derivative with respect to w, so this y over here goes to 0. The derivative of the x times w with respect to w is the w goes away, keep the x. The only weird part there is that we get an x transpose from that derivative. And then we multiply by the contents of the norm over here. So x w minus y, like that. I think that should be what the matrixcalculus.org website gave us. At this point, we're solving for w. So I'm going to, and our left-hand side over here is equal to 0. So I can take away this 2. It doesn't matter. And factor out this x, or distribute this x into the parentheses over here. Get x transpose xw minus x transpose y. Move the x transpose y to the other side. X transpose y equals x transpose xw. And then take a left inverse of this matrix right here, multiplying that x transpose x, the inverse left multiplied, times x transpose y equals w. And so that's my final closed form solution for what the w is that minimizes this ordinary least squares problem before. Again, the textbook also works through this algebra. So if you want a different explanation, that's available in the textbook. This is a very common formula right here. Lots of other, if you just Google like ordinary least squares, you'll get this derivation as a very common result. Any questions though about anything I just did? Yeah, Tyler.
Why is the vector?
Question is y a vector? I guess I think of it as like a matrix that is one-dimensional. The y here is, let's see, how did I actually write it? So y is the d-dimensional vector equal to y. This should be, it's an n-dimensional vector. We have one for one entry in this y matrix for each of our y values. But yes, so here y is this vector where the number of rows is the number of data points that we have. Does that answer the question?
Yeah, I was just kind of wondering why it's capitalized.
Yeah, so why is it capitalized? I capitalized it because I think of it as this, as a matrix. Don't remember how the textbook does it. Good question. So the main takeaway here, the thing that's the most important is this initial step right here of how do you solve one of these argument problems. And you do that by taking the derivative, setting it equal to 0, and then working through a bunch of algebra and calculus. These steps up here, these first 3 steps, the same will turn out to be the same for every machine learning problem. That writing it out as an argmin of some in-sample error, taking the derivative, set it equal to 0, always the thing you do. And then the thing that's different is all this derivation stuff down here. And the reason it's different is because your loss function over here that you're taking the derivative of will be different each time.
Are you guaranteed to get a unique solution to that equation? How do you know you don't get it?
So the question is this solution going to be unique? We'll talk about that probably not fully today, but it turns out that this loss function right here is what's called convex. And anytime you have a convex loss function, you're guaranteed that there's just one global minimum, or every local minimum is a global minimum. And so in particular, in this case, this is the unique global minimizer of this problem. Let's see. So the next problem here, problem 2, what is the runtime of computing the ERM for ordinary least squares? The ERM, I don't know if I've said that phrase specifically yet. That's the empirical risk minimizer. The in-sample error, also called the empirical risk. So the ERM here, empirical risk minimizer is the argmin E sub n. This is a standard term in the machine learning world, also used in the textbook. Risk here, interchangeable with the in-sample error. And so problem 2 here, what's the runtime of computing this? This is asking what is the runtime of this formula up here in blue. The very first notes packet of the class actually had you calculate the runtime of this formula up here. So you've probably done it already, but I'm going to leave this problem. I'm not going to do it. I'm going to let you all do it on your own. But again, what it's asking for, what is the runtime of all these matrix vector products up here? Problem number 3 is the, I guess, first additional interesting problem. And so we talked about, or we just computed the runtime, talked about how to solve for this ordinary least squares problem. But here problem 3 says the VC dimension is undefined for the ordinary least squares problem. And why is that the case? The answer is that the VC dimension is only defined for binary classification. It turns out that there are other types of dimensions that can be used for things like regression problems. But the VC dimension we can't actually use for regression problems. So the only purpose of talking about this ordinary least squares problem was to see a relatively easy example of working through this ERM calculation right here. And that is everything in section 3.2 of the textbook. We're going to go next down to section 3.1 of the textbook. And there's nothing really to write or draw in this section. I just want to highlight a handful of important takeaways and facts. So the first fact up here is that the squared loss is essentially unique. So the squared loss, again, what we were doing just above in the ordinary least squares, it's essentially unique in having a closed form minimizer. And every other loss function, every other machine learning problem that's used in practice does not have a closed form minimizer and requires some sort of iterative procedure to solve. So section 3.1 and 3.3 are going to talk about these other iterative procedures. Section 3.1 talks about the 0-1 loss, so the loss that we've been using so far, and some highlights of this. The 0-1 loss used by the perceptron, again, no closed form solution. And we introduced the PLA algorithm in the chapter 1, but the PLA only works on linearly separable data and will not work on nonlinear data, non-linearly separable data. And in particular, what we talked about is that the PLA will never terminate. It will never converge. It will run forever. There's a new algorithm in section 3.1 called the pocket algorithm, which you'll have to take a look at, but it's essentially just the PLA that runs for a finite number of iterations. And because it runs for a finite fixed number of iterations, it's going to converge. But it's not going to converge to a minimizer of E sub n. And the reason for that is because minimizing this 0-1 loss is NP hard. This is the thing that is the most important to take away from section 3.1 right here. Minimizing the 0-1 loss is NP hard. If you haven't seen NP hardness before, I recommend watching this YouTube video as like a little bit of a background to it. But the idea is that currently the best known algorithms for solving NP hard problems are all exponential, which means that they take omega of 1 plus epsilon to the d runtime. So this epsilon here, epsilon is some constant greater than 0. So this is an exponential right here that's greater than 1, something that's bigger than a polynomial. And the best known algorithms for solving NP-hard problems are this exponential runtime. The way this is going to be important on quizzes is that we assume everybody thinks that there is no polynomial time algorithm for these NP-hard problems, but we don't have a proof. So we think there is no polynomial time algorithm for NP-hard problems. But there's no proof. And so it is an open problem. So far, we've seen only 2 open problems in this class, including this one here. We have this one here and the best possible runtime of matrix multiplication. The only other open problem we've seen is the best runtime of matrix multiplication. So on your chapter 1 quiz, there were a bunch of columns, true, false, and open, a bunch of problems where you could have marked open, but there was definitely no open problems there. Your chapter 2 quiz will also definitely have no open problems, but your chapter 3 quiz will have potentially open problems if somehow it's talking about minimizing the 0-1 loss, because whether a fast algorithm exists for that or not is an open problem. Any questions about that? Yeah. Yeah, so the question is, what is an NP-hard problem? The intuition behind it is just that the runtimes that we have are exponential. The runtimes that we have are exponential. And we think they must be exponential, but there's no proof that that they must be exponential. The detailed theory of NP hardness is moderately complicated, not typically taught in undergraduate computer science programs. Typically in graduate computer science programs, it's taught in full formality. So you're not required to understand the full formality of like what exactly it means for this to be an NP-hard problem, but you are required to know that it is NP-hard, and that means that whether we have a runtime faster than this bound right here is an open problem. Good question. Other questions? Okay. So again, big picture, like what we've done so far, we saw that the ordinary least squares has an efficient solution, efficient way to solve it. But we also, that's not the main problem that we're focusing on, because we've been focusing on binary classification, and ordinary least squares is regression. Then this section 3.1 talks about the problem that we're actually interested in, which is this binary classification, but actually providing the best binary classifier for a linear hypothesis, like the simplest possible hypothesis, that's NP-hard. And so we don't think we have or will ever be able to have an efficient algorithm for doing that. Section 3.3, with this logistic loss, this introduces our sort of efficient ways of actually solving for binary classification. So the idea of section 3.3 is the efficient method for selecting a binary classifier. And so section 3.3 is really all of the computational equivalent to the statistics of chapter 2. Out of these three sections, section 3.3, the most important of these three sections. So what's going on here? Again, I have some text up here, but I want us to focus on these two pictures down here. In section 3.3, there's a lot of pictures about different classifiers or different loss functions. And I want us to draw some of those pictures and talk through them so that you'll be able to make sense of what's going on in the textbook. So yeah, we're just going to skip down here to these two pictures. And what we're going to draw are these two loss functions up here. So this 0-1 loss, like we have traditionally seen it, and this sort of new definition of the 0-1 loss. And we'll see that they are in fact the same thing when they are both defined, but this is a little bit more flexible, this bottom one. So in this picture on the x-axis, I'm going to draw a y hat. So this is our predicted value. And the vertical axis here is going to be our loss function L. And there's two of these graphs. The top graph will do the special case when y equals -1, and the bottom graph, the special case when y equals 1. Because these are two-dimensional variables or functions of 2 dimensions, it's hard to plot them with both everything on the same graph at once. That would be a 3D graph. So we're breaking it up into two separate graphs like this. And so in this case up here, when y hat is not equal to y, that's what we are measuring right here. So y hat can be either 1 or -1. When it is equal to -1, they are the same value. When y hat and y are both equal to -1, y hat and y are both equal to -1, they are the same value, so this thing up here will evaluate to 0. So y hat -1, y of -1, we evaluate to 0 right here for our loss function because they're the same value, and so the indicator here is equal to 0. When they're different values though, when y hat is equal to 1 and y is equal to -1, we'll get a value of 1 for our loss. And so these two blue points are what this function up here is describing, just these two blue points. This loss function down here is a generalization of the loss function up here, where the y hat value is defined for all real numbers. So y hat defined for all r. And under this generalization, we get a sort of step-looking function that, what did I miss? That looks like this. And so again, these two functions, they agree when they're both defined, but this function down here, the orange version, is more general, and so this is more commonly used. More general, so more commonly used. And it totally subsumes this first function up here. The bottom graph looks very similar. I'll zoom out a little bit so we can see them both at the same time. It's very similar. It's just in the opposite direction, that we have y equals to 1 down here, and this is y hat down here. Let me stick with the same colors of blue. When y hat is equal to y, so when y hat equals 1, we get a 0 value for our function. When they're different, we get a 1 value for the function. And so it's defined like that. And then the orange version is defined as a step in the opposite direction. Positives up here, and negatives everywhere else. One of the things that you'll notice about these two functions is that they are symmetric, or if you mirror one, you'll get the other one. And so it's common to rewrite these two functions in a different way using this q value right here. So I've just scrolled down to the next page. The textbook introduces this new q notation, which uses only, it's a function of one variable now instead of two. In this variable z is y times y hat. So the q of 0 minus 1 of z is equivalent. This is equivalent to the orange version of our L01 above. To the orange version of that up above. And it turns out that the vast majority, zoom in one more time, the vast majority of machine learning algorithms can be defined just by specifying what is the q value for those machine learning functions. Specifying a different q will result in a different optimization procedure and result in selecting a different hypothesis from the hypothesis class. And maybe like 20 years ago, nobody realized that. And so everybody was developing these algorithms totally independently. These days, everybody realizes that the q function is all that you need to determine your learning algorithm. And so people only talk about loss functions or these q functions. And there's three important properties that we care about for these q functions. The first one is whether it is a surrogate loss function. So a surrogate loss function L is any loss function that upper bounds the 0,1 loss. So that is, it's always greater than or equal to the 0,1 loss. And I'm going to draw a picture down below to give us an example of a surrogate loss function. So we have another graph like this. Now the x-axis over here is these z values. Again, z is equal to y hat times y. So it's like combines both of the graphs up above that we saw on a single plot right here. And the vertical axis here is the different loss functions that we're going to see. And we already saw that the 0,1 loss has this sort of step shape that looks something like this. So this here in red, that's the 0,1 loss. Another one of these important loss functions is this exponential loss up here, x with negative z. Maybe I'll zoom out so we can see that in the graph at the same time. So this x of negative z right here. We'll plot that, plugging in some values for the z. So if we plug in 0 for z, then we take the exponent e raised to the 0 is equal to 1. So 1 right here. And then as z gets large, as we go to the right on this graph, it's a negative value in front of z, so we get very, very small very quickly with that exponential going very, very small very quickly like that. And then as z gets large negative, it becomes a positive that we're e raised to the positive thing. Again, we get very, very large very quickly, something like this. And so this here is that first exponential loss function graphed. And the first definition that's important about loss functions that we're talking about was surrogacy, whether the loss is always greater than or equal to the red line, whether it's always greater than or equal to the 0,1 loss. In this case, the exponential loss does satisfy that condition. So the exponential loss is, in fact, a surrogate. It does have that property. Were there any questions so far about this picture or what it means to be a surrogate? Andy?
You say again, what's the red line?
So yeah, the red line here is this 0,1 loss. It's literally a plot of this function right here, this q value right here. and its representation is these two versions of the 0-1 loss combined together in one sort of plot, where we're plotting, instead of plotting two separate plots for the y equals -1 case and a separate one for the y equals 1 case, we're plotting them together in one plot by making the x-axis not equal to y hat, but make it equal to z, which is y hat times y. So the x-axis down here is z, which is y hat times y. And you'll notice that all of these loss functions right here, they're written in terms of z, just a single variable that captures both our predicted value and our true value in one value. So yeah, this red, this is the thing that we are actually interested in. This is the whether we got our prediction correct or not. If we get our prediction correct, then the loss that we suffer for that is 0. We suffer no bad consequences for getting our loss correct. But if we get our loss value incorrect, so if y hat and y multiplied together have a negative value, then our 0-1 loss gives us something negative, gives us a -1. And so the red value, that's the thing that we're actually interested in. That's the traditional out of sample, or the error, whether it's out of sample or in sample, that we've been talking about so far, has always been the 0-1 loss. And this blue line is an alternative possibility for a loss function, in this case, the exponential loss. So this table presents a handful, 6 of these important loss functions. All of these have been proposed at different times as being state-of-the-art loss functions to use. At this point, the only 2 that are commonly used are the logistic and the hinge. The other ones are no longer state-of-the-art for anything, but logistic and hinge, state-of-the-art for very many things. SOTA, state-of-the-art, sort of the best possible things that you can choose. We'll spend a little more time here in a minute talking about this table and talking about these other properties of convexity and robustness. But first, I want to think more about, why do we care about the surrogate loss? Why do we care that something is a surrogate? Why do we care that the QZ value for that loss function is greater than or equal to the 0-1 loss? And to talk about that, we're going to come down here to problem 5. So problem 5 says, let L be a surrogate loss function for L01. So it's upper bounds are 0-1 loss, and derive a VC generalization bound for the generalization error E out minus E in. The difference between this generalization error and the ones we've seen before, though, are there's 2 separate loss functions. What we've seen in the past is that E out loss 0-1 less than or equal to E in loss 0-1 plus the big O notation stuff of square root dVC minus log delta over n. And by the fact that L is a surrogate, we have that so this is the surrogate. What surrogate implies is that the E in of L01 is guaranteed to be less than or equal to the E in of our surrogate loss, L. The example we had above being the exponential loss. And so we can plug this inequality in right here, plugging in E in of L right here, and the final inequality stays the same. Doesn't affect our inequality at all. E out L0-1 now less than or equal to E in of L plus all this generalization stuff, square root dVC minus log delta over n. And so if there's a way for us to optimize this surrogate loss, then we still get good bounds on our error rate or our accuracy out of sample. If we get good En sub L, our in-sample error, with this other modified loss function, we get good out-of-sample error on the loss function that we care about. Good out-of-sample error on the 0-1 loss. And so this right here, this is why we care about surrogate loss functions. Next time in class, we'll talk about how some of these surrogate loss functions, what properties they can have, which will make it easy for us to compute the in-sample error of those surrogate loss functions. But the fact that it's surrogate means that if we can get a good in-sample error, then we will also get a good out-of-sample error with enough data points. Yeah.
So why don't we include the log n in the equation for the
Yeah, that's a good question. So the question is, here in the generalization bounds, I've been eliding the log in factor right here for two reasons. One is that so this, what the textbook shows is in fact that we have a log in the numerator. But it turns out that there is a better bound that does not have the log in the numerator. And so this statement over here is also a true statement. That true statement is the one that I'm more familiar with, so I'm more likely to just, it's a better bound, so that's what I use when I use these things. The log in factor up here is also, though, essentially inconsequential because log in grows so slow compared to in. And so if we wanted to make this be technically correct with the textbook's notation, there's a version of the big O notation. If you add a tilde on the top, the tilde ignores log factors. And very common to ignore the log factors just because they grow so small. So it's not wrong to include the log in the top of these generalization bounds. The textbook does it, but it's also not needed because you can either ignore them with the tilde over here or just acknowledge that there is a better bound that does not have the log in on top. Does that answer your question?
Yeah, but if you're ignoring log factors, then why wouldn't you?
And then the question is, why not ignore the second log? So very often I will also write the O of if we don't care about the probabilities. Very common to also write something like this, that the generalization error is equal to root DVC over n. It's also a common thing to do. Yeah, Kevin.
Is there any log function that the log 0, 1 is for?
Loss function that the 0, 1 is a surrogate for? Can you say it again? Yes. Oh, so the question is, could this red line right here be a surrogate for something else?
Yes.
So technically, mathematically, it could be, but really the red line is the thing that we actually care about. So we never talk about the 0-1 loss as being a surrogate for something else. We only talk about something like the exponential loss being a surrogate for the 0-1 loss.
And we're trying to get as close to the 0-1 loss.
Yeah, so this brings up the question is like, what makes some surrogate losses better than other surrogate losses? And we'll talk about this more detail next time, but there's these other two properties right here about whether a function is convex or whether a function is robust. Intuitively, what convex is going to mean is that it's going to be easy to optimize, that we're guaranteed to be able to find the minimum of the function. And so here a loss function is convex if the line segment between any 2 points on the graph of the function lies above the graph between the 2 points. This exponential loss is in fact convex because if I draw a line like this, no matter where I draw it, it's above the graph. So this is in fact convex. Is it robust? Well, the definition here about robust is that the closer a loss function is to the 0, 1 loss, the more robust that loss function is. The exponential loss, very much not robust because the 0, 1 loss here stays at 1 forever, no matter how far away you get from the origin, but the exponential loss grows out very, very large very quickly. So it was very not robust. These state-of-the-art, like logistic loss and hinge losses, what they end up looking like is, I'll do orange for the logistic loss here, is it's a straight line like this to here, and then a very light curve coming down like this. This is the logistic loss, often just called the log loss. And the hinge loss looks similar. Hinge loss is straight line up to here, but then the straight line keeps going all the way to the origin and then becomes perfectly flat. So again, in the magenta color here, that's the hinge loss. Both of these two functions are surrogates still. They, so surrogate, surrogate. They're also both convex, convex. They're a little bit robust. I'll say robust-ish, robust-ish, but they're not, like they're more robust than this exponential loss, but they're not super robust because as we get far away from the origin here, this value over here is still very far away from the 0, 1 loss down here. A more robust loss would be this smooth 0, 1 loss. Actually, we'll do the trimmed hinge loss right here. It's easier to visualize. And we'll do this in green. The trimmed hinge loss agrees with the hinge loss everywhere, except once we get below the -2 value here, we stay at 2 forever. So this trimmed hinge loss, this is very robust, but it is not convex, but it is a surrogate. So this trimmed hinge loss, it would be like the best thing to use. It's very close to the 0, 1 loss, and people do use it for certain things, but it's not convex, and so we'll see that it'll be hard still to optimize. The logistic loss and the hinge loss, the reason why they are state-of-the-art for different things is because they are as close to being robust as you can get while maintaining both the surrogate and convex properties. Yeah, this plot right here will be very important for you to understand, for you to have an intuition about what all 6 of these different loss functions, what they look like, and these 3 properties up here, whether they're surrogates, convex, or robust. So I haven't done the smooth 0, 1 loss or the squared loss, but you should hopefully be able to do those yourself at this point. And next time we will be building off of this to talk about why. So we talked already about why surrogacy matters. Next time we'll talk about why convexity matters and how it actually lets us generate an algorithm. That's it for today, though. If you have more questions about any of this or anything else, I'll stick around to get those answered. Otherwise, I will see you next. I guess I have office hours on Friday like normal. So you're welcome to come to those. Otherwise, I will see you next Monday.